Okay, we'll be talking about chapter 29, 30, and 31 today, starting with electromagnetic induction. What electromagnetic induction is essentially says that a changing magnetic field is going to induce a EMF or a potential. Special name for that is Faraday's law, so we'll talk about how to go ahead and calculate the EMF, how to determine the direction, and how a changing magnetic flux generates an electric field. And lastly, we'll talk about four very important, very fundamental equations that describe both electricity and magnetism. So kind of the marriage between electricity and magnetism. So very important concept here. Now this idea of induced current and induced EMF was actually determined experimentally. Now think about a couple of scenarios here. One where we have just a simple bar magnet and we're holding it near a coil of wires. This coil of wires is hooked up to an ammeter. It's going to essentially measure the current that's flowing through these loops right here. Now we know that there's some magnetic field that's coming away from this guy, so some flux going through this coil. Keep in mind, however, that if we just have a stationary magnet, then we're not going to see any current reading in that coil. So this guy right here is simply going to read 0. However, if we were to take that magnet, the same exact magnet, and wiggle it up and down, so get some motion going in that direction or in that direction, well, here's the magnetic field going away from the north coming into the south, and essentially we're changing the magnetic field that is penetrating this coil of wires right here, and so we're going to show some non-zero current. Similarly, we know that if we took a battery and we hook it up to a coil of wires right here, we're going to generate a magnetic field. It's going to look just like a bar magnet, and if we were to move that similar setup through this larger coil of wires, then the ammeter is also going to be reading a non-zero reading. Another way that we could read some current in this ammeter right here is to have this secondary coil right here inside of the first coil, and then have that hooked up to a battery, but have a switch that we could open or close. Essentially what we would then be doing is we would be turning the B field on and off. All three of these actions are going to read some non-zero reading of current in this coil of wires. What they all have in common is all of them are causing the magnetic field in the coil to change. Changing magnetic field is going to cause an induced current and an induced EMF, or an induced voltage. Just a reminder from chapter 27 that we can talk about this quantity called magnetic flux, and magnetic flux was going to be equal to the circular interval of magnetic field dotted with area, and the unit for that guy was Weber. What we're really talking about when we're talking about induced current and induced EMF is we're actually talking about a change in magnetic flux more than we're talking about a change in magnetic field. You can kind of see here that by changing the magnetic field or changing the area, both of these are going to cause a change in the flux. Now this leads us to the very first important law that we're going to talk about, which is Faraday's law. And what Faraday's law says is this induced EMF in a closed loop, it's going to be equal to the negative time rate of change of the magnetic flux through the loop, or this little squiggly script E right here is going to be equal to negative d flux dt. Now keep in mind that the demagnetic flux is going to be equal to magnetic field dotted with some tiny little bit of area. We could go ahead and rewrite this guy be equal to negative d dt of the magnetic field multiplied by the area, if we're talking about some large amount of area right down here like A. We could also write this guy as being equal to negative area changed magnetic field changed magnetic field over time plus the magnetic field and change in area over time. The key idea is either the magnetic field can change and the area can remain constant, or the magnetic field can remain constant and the area can change over time. both of these guys are going to induce an EMF, or induce some voltage or potential, if you will. So take a look at this example down here where the magnetic field is going to remain constant, and what's going to change is going to be the area. That's going to change the magnetic flux. So the magnetic flux initially is just the magnetic field multiplied by area, and then we rotate this plate a little bit, and then this dot product is going to yield magnetic field area cosine of the angle in between them. And then once the plate has essentially rotated 90 degrees, then the magnetic flux is 0. So we're having a changing magnetic flux, and so along the edges of this guy, if there was a conductor, we would be inducing a current. Taking a quick look at example 29.1, we're going to have some coil of wires that's going to give us some area right there, and we're told that we have a time-changing magnetic field, and what we're asked to calculate is we're asked to calculate the induced EMF and the current read by this ammeter right here. We know that the resistance in the circuit is 5 ohms, so what we can say is the induced EMF is going to be equal to the change in magnetic flux divided by the change in time. In this case, area is not changing, and so we have area multiplied by changed magnetic field divided by time. So 0.012 square meters multiplied by 0.02 Tesla per seconds is going to give us our EMF, which is going to be 2.4 times 10 to the negative 4th volts. That's the induced EMF, and then we can say that the current is just going to be equal to the induced EMF divided by the resistance given right here. Now, what I haven't discussed is that negative sign, which should have been right there. Hopefully you were paying attention. I'll talk about that on the next slide when I talk about the direction of the induced EMF. So now let's talk about the direction of the induced EMF, and a very, very, very important slide to be able to calculate the direction of induced EMF. We'll actually talk about even more on the next section when I talk about Lenz's law. Now, thinking about the EMF as the negative time rate of change of the flux, and we know that the flux is going to be equal to essentially B dotted with dA. In this case right here, we have B and A in the same direction, and the magnetic field is increasing, so it's going from a shorter arrow up to a larger arrow, so the flux is indeed changing. The flux is going to be positive. B and A are in the same direction, and it's becoming larger and larger and larger. B is becoming larger, so the flux is becoming larger. The change in flux is greater than 0. That negative sign right there means that the induced EMF is negative, or in the clockwise direction. Remember that from torque, clockwise is going to be negative, so clockwise is going to be negative. If the magnetic field is decreasing for the same type of scenario where B and A are in the same direction, then the flux is going to be positive, and it's becoming less positive, it's becoming smaller and smaller and smaller, and the induced EMF is going to then be larger than the 0, and so it's going to be in the counterclockwise direction. Similarly, if B and A are in opposite directions, and B was to be increasing, well, the flux, B and A are in opposite directions, so the flux is going to be negative, and it's going to become more negative because B is becoming larger. Then the induced EMF is also going to be positive, or in the counterclockwise direction. And lastly, if they're in opposite directions, the flux is indeed negative, and it's becoming less negative, so the change in flux is going to be larger than 0, then the induced EMF is going to be negative or in the clockwise direction. Again, make sure that this is in your head, please. The direction is very important. So let's take a quick look at a real-life application, or a sample alternator or generator, if you will. Kind of following example 29.3 here. What we have is we have a loop of wire that is going to be in a magnetic field. It's going to be turning about some axis. You can see that this side of the loop is connected to this terminal over here, and this terminal does not touch that, but that side of the wire is connected to some other terminal that's not touching terminal A over here. If we were to look at this loop end on and look at it over time, then we're going to see it has some maximum flux at, say, some initial position where it's going to be the magnetic field multiplied by the area. Right here, it's going to have zero flux because the magnetic field and area are in opposite directions, so there's going to be zero flux. So we can kind of see the change in flux over time. It's going to be sinusoidal. If you were to look at the change in flux over the change in time, well, that guy is going to start off being zero, and it's going to have a maximum when the flux is going to be changing the most rapidly, which is actually going to be when it's going from the horizontal position to any of the other positions around it. That's when the area is going to change the most, and it's also going to look sinusoidal. We can write that induced EMF to be equal to the angular frequency multiplied by the magnetic field multiplied by the area, and then sine omega t. Now, this type of EMF that is constantly changing, this voltage that's constantly changing, that means that the current is going to be constantly changing. And so the type of current that we're going to be generating is going to be AC current or alternating current. This is the type of current that you have in your household. We can look at a similar example where we have the same coil of wire and it's in a magnetic field rotating as it was before. But for this example right here, rather than have the two coils connected to two brushes that remain the same, here we have a little gap right there that essentially, when this loop is going to be straight up and down, it's going to switch the terminals such that the induced EMF is always going to be positive. If we were to look at the flux over time, it's going to do the same thing that it did before. It'll be looking like a cosine. The induced EMF is going to only be positive in this case. It's going to kind of hop up and down just like that. What we can then do is we can add a couple more components to smooth this guy out, and we would be able to produce a DC current or a direct current, which is essentially going to say that EMF is going to be equal to some constant over time. So kind of like a car battery. It's going to be a constant 12-volt circuit. This slide wire generator shown in example 29.5 is an excellent conceptual example where we have the magnetic field is going to be a constant directed into the page, and the area is going to be also directed into the page. What we are doing is we're taking this this little bar right here and we're sliding it with some velocity. What that's doing is that's changing the area. The magnetic field is going to be constant. Remember that the induced EMF is going to be the negative change in magnetic flux divided by the change in time. And in this case, magnetic field is going to be constant, so it's negative magnetic field dA dt. Well, how much did area change by? Well, it changed by essentially this much, which is related to the velocity multiplied by the amount of time, the time step dt, and then the length. So the change in area, that's simply going to be equal to the velocity dt multiplied by the length. So we have negative magnetic field, and then dt, velocity dt multiplied by length. And there's a little bit of mathematics here, but these dt's are essentially going to cancel out, and we're left with negative magnetic field, velocity, and length of the wire. It's going to be the induced EMF. The negative sign means that it's going to be in the clockwise direction. Now, if you were really on the ball, you'd be saying, hey, wait a second, we've gone ahead and we've induced a EMF, we've induced a current running through this circuit right here, and I remember that the force is going to be equal to I L crossed with B. So if I do my L crossed with B, I can see that I'm going to have some force now in the backwards direction that's opposing this motion right here, and it's related to the velocity. So all these guys are kind of all intermingled here, where the faster the rod goes, the larger the induced EMF, which is going to be a larger current that's introduced, and also a larger backwards force, which is opposing the motion in this slide wire generator. So let's take another look at this direction of induced current. So a very important slide is going to be called Lenz's law. Essentially, if you weren't too happy by saying the induced EMF was equal to the negative d flux dt, if really that negative sign tells us the direction, if you weren't happy with how we came up with that direction right there, Lenz's law gives us another way to figure out what the direction ought to be, and then we could just calculate the electric flux and apply it and find out the direction on our own. Essentially, what the direction of any induced magnetic effect is going to be opposing any change that's happening. So opposing the cause of the effect, if you want to follow what the book says. Now, let's take a look at just a coil of wire. What Lenz's law says is this wire is happy the way that it is. It's happy just kind of sitting there with some constant magnetic field at some given instant. If the magnetic field were to suddenly increase, then there's going to be a change in magnetic field. Any induced current is going to oppose that change. So the induced magnetic field must point in the downwards direction, so in the opposite direction as the change. So kind of that word oppose right there. Now how do you go ahead and you get the magnetic field in the downward direction? Well, you point your thumb the downwards direction, and then you say, which direction do I need to curl my fingers in? Well, I need to go ahead and I need to curl my fingers in the clockwise direction to get my induced magnetic field downwards. So the current and the EMF that are induced are going to be in the clockwise direction. Let's kind of take a look down here where we're going to have a magnet that's falling through a coil of wire. You know, we know that the magnetic field always points away from the north end, and so as it falls into the wire, the change is going to be in the downwards direction. So the induced magnetic field must therefore be in the upwards direction. Point your thumb, curl your fingers, and you can see that the induced current must be in that direction. Similarly, if we had the south end of a magnet and we pulled it away from it, the change is going to be in the downwards direction. So the induced EMF is going to oppose that change, must therefore be in the upwards direction and have the counterclockwise current. You can also convince yourself in C and D that the change is going to be in the upwards direction. Therefore, the induced magnetic field must point in the downwards direction. Point your thumb the downwards direction, curl your fingers, and you get the direction of the current.